Hello everyone. Today's topic would be on Gauss-Elimination Method. We have seen earlier at least one method to solve a system of linear equations of algebraic equation, I would say, and turn them into a matrix form, and then proceed to these concepts that we are learning right now in engineering maths. And Cramer's rule was the first method we have used, and this was basically about using determinants. Now today I'm going to show you how to use the Gauss-Elimination Method. This method has many applications in engineering or economics, so it would be useful for anyone, not only for my students, those doing the engineering maths module, but it could be useful. So let me start today. Before, I'm going just to rewrite the algebraic equation to explain it, and then we are going to see a meaning of homogeneous system or non-homogeneous system. So today's topic is on Gauss elimination method. Okay, so first of all, let's see how we are going to write, how you will have algebraic equations given to you. And I've just give a generalized form for unknowns. So we're talking about unknowns, usually denoted by, I would say, x. So these are your unknowns. Now, an algebraic representation would be that you are going to have, let's say, a11 x1 plus a12 x2 plus plus a1n xn to be equal to b1. So this is our first equation, I would say. Now second equation is a21 x1 plus a22 x2 and so on. You have got a2n. So I think that you have figured out by now how you obtain this sequence of, I would say, subscription values. So this goes on, I would say, let's say we have m equation. So you have am1 x1 plus am2 x2 plus ... and then you are going to have amn xn to be equal to bm. Now you have these algebraic equation. You can easily have the matrix form for these type of equation, and specifically in textbook they give the matrix form in as ax to be equal to b. So this can be denoted as a vector. This is a vector, and this is of course a matrix. So what we need is, you understand that for the matrix A, sorry, let me just fix this. So for the matrix A, you're going to have all these A values here. These would be your entries in your matrix. And then for the matrix, of course, for this vector x, this would be your unknown. So these would be your x. Of course, these are your x. I'm not going to have to show you how to write this in matrix form. I'm just a recapitulation of what we have done. And you have these are your, I'm sorry about that, you have these to be your b vectors. So you have these values. So in fact, is that you're going to have this A, matrix A, vector x, and equal to b. Now, we are interested in the vector b. So again, just a recap. Now, the vector b, values for these entries that you have in the vector b, these values b1, b2, bm, it gives you a name that you can name your system, I would say, of linear equation, of linear system. Now usually if you have got all of these b values, that is b1, b2, bm, so let us write as first node. So if all, let us write it as bj, if all bj for j to be equal to 1, 2 till m, they are actually zeros, then this system that you have, this linear system, is called, I'm just going to write this, linear system is called a homogeneous system. Okay, that is your b vector, simply has values of 0. Right? Now, second note, again with respect to these b values, if you have got at least, let's say, at least one of these 0 here, let me just have this one of these 0 here, it could be a number, any number, let's say 0, 1, and all of these are zeros, but because of this one here, you can't say that your system is homogeneous. This would have to be a non-homogeneous system. So at least one of the bj, at least one of these values, they are not equal to 0, then you name your system to be a non-homogeneous. Right? So now let me just have this non-homogeneous. Okay. Now one thing again about the homogeneous system is that let's say if you have got, let's say you have got this matrix form. Okay, so this is our 0 matrix. Let's just write it as a 0 vector so that you understand that it is the b which is actually 0. So let's say you have got a system like this. You have got a matrix time an unknown, and this is equal to 0. You will have at least one solution, I would say. So there is at least one solution will exist. For homogeneous system, you are going to have at least one solution, and this would be the trivial solution. That is, all the x here, all these x unknown, they're actually equal to 0. This is our trivial solution. This is the only possibility. So it's simply, I just want you to understand that if a system is homogeneous, you are going to have at least one solution, which is a trivial solution. That is, all the x values are going to be 0. Okay, so now before I just proceed to one example on the Gauss elimination, we're talking about solution. Let us just have a look about the types of solution, different types of solution. So actually we have 3 types. I know that all of you, you understand, you have done that already, but I'm just doing a recap because I want you to figure out the importance of knowing all these before we proceed to the method of solving a system of linear equation. Now, we have 3 possibilities. First one is that I'm going to have a unique solution. So let's say in this case, whenever you have got a system ax equal to 0, x equal to 0, it is actually the trivial solution, but it can say that it is a unique solution that you can have. Second type of solution is that you have infinitely many solutions. Thirdly, finally, is that there is no solution. Okay, so now actually this part here, it would be more understandable if you can say if we have seen a rank and consistency, but I'm not going to do that today. Today is about Gauss-Elimination Method, so I'll just do another video on the meaning of rank and consistency. Now, just to have a look about these unique solution, I'll just give you a simple example, on, so that you understand what you have done in geometry in lower secondary. So let us say the case one, I just want you to consider, let's say, a system like this. So you have got the A matrix, which is 1, 2, minus 1 here. Then I've got the B, which is 1, 0. And then the unknown is, actually you have got two unknowns. So you can easily rewrite this in terms of algebraic equation, and by doing so you will see that you have two equations where what you have learned in geometry is that whenever you plot these two equations, you sketch them, you will have only one point of intersection. So this is I would say a unique solution. I'm not going to do the sketch for you. So just want you to understand that within this system you have this matrix, and you may write this again as a linear system of algebraic equation. Now this is your first equation and the second equation. So what I said is that you can easily sketch these two equations, and then by doing so you will see that there is only one point of intersection, and this is what you have done in geometry. Now this gives you actually a unique solution. And eventually I talk about rank and consistency. It means that simply you have got a solution to be consistent. So this type of problem here is consistent, you can say. Case 2. Let's see the case 2. So I'll just write a 2 by 2 matrix, and just to have a better idea. So let us say now I want this to be written as a system of equations. So you're going to have x1 plus x2 to be equal to 1, 2x1 plus 2x2 to be equal to 2. This is the first equation. Second equation. Now you can say that when you're going to plot this graph, to sketch these two equations, you will have these two lines to coincide. And actually when two lines coincide in geometry again, this gives you a meaning that you have got infinitely many solutions. Last case. So you figure out that this is about having no solution at all. So let's say I'm just going to use a matrix. So 1, 1, 1, 1, and then the B is 1, 0. Okay. So again, having this written as an algebraic form, you're going to have x1 plus x1 to be equal to 1, x1 plus x1 to be equal to 0. Now this is quite easy to understand, because plotting these two graphs will give you two parallel lines, and having two parallel lines, there is no intersection at all. This gives you no solution. So basically this is what you have seen in geometry in lower classes. And I'm sorry, and for case 2, now case 2 is simply that your system again is consistent, because you're going to have solutions for them. This one is inconsistent because there is no solution. Okay, so let's now see actually what I'm here today is about solving a system using the Gauss-Elimination Method. Now just a recapitulation on Gauss-Elimination Method. We have seen row operations, how to convert, I would say reduce a matrix in a row echelon form. This is by going through elementary row operations. So either you add a scalar with a row, you scale a multiple with the row, you add it with another row. So you have got many type of elementary row operations. So you see what you can use. I'm not going to give example on row echelon form. I'm just going to proceed to the example, and then we shall see again how to do the row echelon form. So let me just write an example for you. So I want you to solve this system. Minus x1 plus x2 minus x3 equal to 0. And so see that I'm going to write, I would say, in order, because this is one principle that you as a student of maths, is rewriting equations in order. That is, when I say in order, because I don't want you to make mistake to write them again in terms of a matrix, because I want to have this form, this ordered form. That is, you have got x1, x2, x3, x1, x2, x3, and you don't have any x1 here, so you don't write anything, but I want this to be, you know, just one below each of the. Now you have got 20 x1 here plus 10 x2, and there is no x3, and this is equal to 0. So actually, if there is no x1, the coefficient is 0, and here if there is no x3, the coefficient is 0. Now you can have this system to be written in terms of a matrix form. Now remember that I want the matrix A to have coefficients. They are actually the coefficient that you have with your unknowns. So I'm just going to have this here. This highlighted in orange would be my matrix A. So in matrix form, you have quite easy to write in matrix form. So actually this is 0. And then this would be your x, your unknown, and this is your b. So clearly this system is non-homogeneous because we have got values here. This is 0, this is 0, this is fine, but this is 90 and 80. These are two values. So at least one of them is not 0, then we can say that the system is non-homogeneous. So clearly this system here is non-homogeneous. Okay. So what I want you to do is, I want you to, so now we are going to solve it, and we are going to use the Gauss-Elimination Method. Now, what we are going to do is we are going to write an augmented matrix. So what is an augmented matrix? We have the matrix A here, we have the matrix B here. We are going to merge these two matrices to have an augmented matrix. So actually, this is, you can label it as C. So the augmented matrix C, let's say, is going to be the matrix A with B. So meaning that I'm going to have a matrix in this form. These are my matrix A entries here. And these are my B entries. Okay. So this is what we call an augmented matrix. Now, let's proceed to the row echelon form. Now, you should understand one thing is that what we are doing here is the Gauss-Elimination Method, also known as row reduction method. Now, why row reduction? Because basically we are going to use elementary row operation to reduce this matrix here in a row echelon form. Now, for those who have forgotten what is a row echelon form, is that we want a matrix, a diagonal matrix, upper triangular, okay, having values, upper triangular values like these. These are given as values, and all the lower entry that you have is going to be 0. So this is actually a matrix in a row echelon form. Now, procedure is that you need to have a leading coefficient. A leading coefficient would be having a pivot. So what I do is I would choose this first one value here, this first entry here, as being my pivot. And the aim is to have below this first pivot here, the aim is to have the free values, or whatever values are below this, the pivot, it needs to be 0. Okay, so this is the first aim. This is how you proceed with the row or echelon form. So firstly, let me just label the rows. So this is my row 1, this is the whole row 1 here, this is row 2, row 3, and this is row 4. Now you can see that for this example, I have 1 0 here, so this is fine for me. We just need to work out with the R2 and R4. So this is your second row and the fourth row. So what we do is you find a way that I can have 0 here. So this is by manipulating actually your the rows. So what I do is with this R2, I just need to add R1. Why? Because you can see that I want this value here to be 0. I want this value here to be 0. Okay, this is my aim. We want this to be 0. It's not 0 factorial 0. So what we do is you find a way by manipulating these rows R2, R1, and then you have this value to be 0. Now understand that sometimes it is quite, I would say, this is a principle so that you use the row where you have got the pivot value. Okay, so because my pivot is 1, which is in R1, in row 1, so I'm going to use the row 1 just to manipulate this R2 so that I can obtain 0. So this is one principle, I would say. Then before I just proceed to the simplest form, you see that you have got, just have highlighter here. So I have got, so this is 0, this is fine for me. I need to convert this 20 also in 0. This is the aim. So again, manipulating your rows, R4, using your R1, the pivot row, I would say. So you just see that you can have R4 subtract 20 R1. So you can have a scalar multiplication here, and then you have a row operation that is a simple row operation, you know, and addition and subtraction, and then you simplify this augmented matrix. So simplify, and one thing is very clear is that this is not going to be equal to the form, simplest form here. It is not equal. You don't write equal, just write the matrix, the simplest form that you have here. So we have 1, because I just want all these to be 0, so 0, 0, 0. So this is the whole R1 is the same. Now you see that you have got R2 here, so this is actually R2 plus R1, so you have minus 1 plus 1, which is 0, 1 plus minus 1, which gives you 0, minus 1 plus 1, which is 0, and of course this is going to be 0. The R3 is the same because this is already 0, this is fine for us. And then here you have got 20 minus 20 times 1, this gives you 0. And then 10 minus 20 times minus 1, this will give you 30. And then you have 0 minus 20 times 1, this is minus 20, and 80 minus 20 times 0, this gives you 80. So I'm just going to write this with my blue pen. So again, this is, I would say, first step for row echelon form is that below this diagonal, because understand that a row echelon form is that I need to have values below my diagonal to be 0. So this is my diagonal. These values here should be 0. This is the aim. You have an upper triangular matrix with value entry of 0 here. Now let us just write R1, R2 here, R3 and R4. Now you can see that for this example I've got the row 2, which is actually all 0 values, and I know that which is most important in a triangular is that I have at least these 3 entries here, they need to be 0. So you can just, I would say, change places. You can have you can interchange these rows. So what I'm going to do is I'm going to send this up, the R3 and R4, and then I'm going to have this R2 here. So let me just write again my matrix. So you have the 1 minus 1, 1, 0. And then you change it, you change these. So this is going to be 0, 10, 25, 90. This is 0, 30, minus 20, 80. And this is 0, 0, 0, 0. Okay. So interchanging the rows, and then you have a different R2, R3, R4. Okay. So this is fine for me. I've got these 0, these are 0. So I just need to work with this value. Well, don't forget, you always figure out where your diagonal is, and you see that I need to have this 30 here to be 0. Okay. So what you do is, because you are changing now, you're going to have another leading coefficient or pivot. Now 10 is going to be your pivot. So actually the pivot would be the value that you have in your diagonal, and this is in order. You work with the first pivot, have all these values 0, second pivot have all these values 0, and if needed, this pivot here have this value to be 0, and then you are done. Now sorry, now I need to have this value here below my pivot 10 to be the 30 to be equal to 0. This is my aim now. Again, elementary row operation. So what can you do with the R3 is that, very simple, you can have R3 minus 3 R2. So 3 times R2. Okay. So let us have again the reduced form of my matrix. Okay, so let's have to see this one. So actually these are 0, so whatever type of operation you do, this would be actually 0. So you get 30, so R3 minus R3 R2, 30, minus 3 times 10. This is going to be 0. Minus 20 minus 3 times 25. This is going to give you minus 95. And then you have 80 minus 3 times 90. This is minus 190. And you have the fourth row, which is actually 0 values. Okay, here you are. So we have got we have obtained the values below the diagonal to be 0. So you have, these are the values. Sorry, I should have written this minus 95 here. Okay, so all these are 0. So this is the reduced form that you can have for a row operation. So this is actually in row echelon form. Okay, So now the aim is, the Gauss elimination method is that you have the system, you have the augmented matrix, and then you reduce the matrix by using elementary row operation, and then you have a row echelon form. So actually, when we have started with our question here, the question was to use the Gauss elimination method to solve this system. And when you obtain this reduced form, sometime in some textbook, they name this now to be a Gauss-Jordan elimination, because we have reduced it. In the reduced form here, you can name it as Gauss-Jordan elimination. Now, why we do that is because now you're going to have a simple system of linear equation, a simple one, because you can solve them easily, I would say. So what happens is that having this form here, don't forget that this is actually the entries in your matrix A, and this is the entries in your matrix of vector B. Now what happened is that reduced in this form, I have now a system of linear equation given like this. Here is your free equation. So you see now this is easier to solve. So you just need to solve it using backward substitution, back substitution, and then you obtain your answers for the unknowns. So I've already done that. You can just do it and verify your answers. I don't want to waste time. So actually backward substitution is that you start backward here, and then you solve by having the value of x3, x2, and x1. So you're going to have x3 to be equal to 2, x2 to be equal to 4, x1 to be equal to 2. This is the Gauss elimination method. So here you are. My next video would be on rank and consistency, and then we shall see another method on how to solve this linear system of equation. This would be your LU factorization, right? So okay, thank you.